Okay, so as I mentioned in our last class, I haven't yet graded the tests, but my goal is to have those finished on Friday, and then we'll go through the solution for exam 2 during Friday's class. Um, your next homework assignment is due before class on Friday, and that's the one where it's just 2 problems. The first problem is a bundling and budget limitation problem. Almost identical to the concepts that were in the in-class exercise from Monday's class. And then the second problem on homework 11 is kind of just some personal finance stuff that is to whet your appetite for the project. I got a good question about that second problem. Someone was asking about the tax. And they were asking, does the tax apply just to the income that you've made from working that year, or is the tax also applicable to your earnings on savings? And what I told that person and what I suggest for you is only apply the tax to the earned income. For the majority of people, the bulk of their retirement savings are in tax-deferred accounts where you don't pay tax on the growth each year. You pay tax when you withdraw the money during retirement. And so on homework 11, problem 2, just apply the tax to the money you get from working that year and assume that your interest on your cumulative savings balance grows tax-free. Okay, so like I said earlier, that problem 2 is just to kind of get you thinking a little bit about the spreadsheet that you have to include on the project. And speaking of the project, we are now down to 2 weeks. You've got 2 weeks to finish it. So I hope that I'll be getting lots of questions, and that's an indicator for how much students are working. If they're asking me questions, then I have an idea that people are engaged. Today we're going to be talking about some kind of concepts that are more on the economics side of things. You know, in this class we do a lot of analysis and problem solving and decision making. And we have a couple of lectures that are more just the pure economics of things. And that's kind of what we'll be covering today when we talk about price, demand, and break-even relationships. Before we begin on that, are there any questions related to the announcements? All right. Well, I'm sure that everybody here at one point or another has seen an advertisement like this. And one of the times that I see a lot of these is at Thanksgiving. And maybe the only time each year that I go and buy a newspaper is on Thanksgiving Day, because that's where you can go get all of the glossy ads that are talking about the Black Friday sales. And so if you want to know, for instance, who's got the cheapest $5 waffle iron for Black Friday, then you can go buy a newspaper on Thanksgiving and find that all out. So, and in fact, I got real lucky last Thanksgiving. Just kind of coincidentally, I walked into Walmart in the late afternoon of Black Friday. I think I was going just to, pick up some lettuce or something, but they had just brought out a big crate of flat screen TVs, and I got a 55-inch flat screen TV for my parents for $150. So this is from a few years ago. Back then, all $150 would get you is a 40-inch TV, but nowadays a 40-inch TV, you wouldn't give that to your dog, right? You gotta have 55 inches minimum. So that's what I got. Anyways, the point of this is just to illustrate that low prices stimulate demand. So people line up in front of Best Buy for these low prices. And so it's how you can control how much of something people are interested in buying. Now there are other factors as well, for instance, like the quality of your product. Sometimes people will line up to buy a new iPhone because they're iPhone fanboys. Is that what it's called? An iPhone fanboy, where you line up and can't wait to get the next iPhone? My brother's one of those. But sometimes you have like a unique or a product that competes just on the basis of its quality, but far more commonly, the only tool that you have at your disposal to stimulate demand is by lowering prices. By the way, there are some other effects that come from being known for having consistently low prices. Amazon is kind of the dominant retailer in the United States these days. And each year it seems to be earning record profits, especially during the pandemic when a lot of people were nervous about going out and shopping in person. And that's changing a lot of things about our economy. There are stores that used to exist that don't exist anymore because of Amazon's ability to undercut the competition. When you don't have a retail location, like Toys R Us, for instance, what does Toys R Us have to do? They have to pay rent for their retail facility. They have to heat that retail facility. They have to pay for the lighting. They have to keep inventory on the shelf. Even if it's selling slowly, they're committed to having stuff in stock, whereas Amazon has this more nimble supply chain, and they have things coming in maybe just hours before they're sold, so they're keeping their warehouse relatively smaller. They can keep things packed together in a smaller space because it's robots that will bring the shelf to the pickers, and so they don't need to have space in between each aisle for a shopper to walk up and down the rows. So Amazon is able to undercut the prices, and sometimes they sell things at a loss just because they can, because they've got such a huge market capitalization that for many years, I think for more than a decade, Amazon was selling things at a net loss. They were losing money, but then they just became dominant and have kind of taken over retail in a lot of ways. So what we're going to be talking about today is the relationship between price and demand. And so we consider price to be an independent variable, meaning it comes into the relationship. That's the thing that a retailer or a manufacturer has control over, is what they charge the customer. They set the price, and in response to that independent variable, the dependent variable is the demand that results. And so the public will respond to you charging a certain amount for your product with a certain level of demand. So if you have a smartphone and you want to charge $100 for it, that may be a really compelling price point and you'll have a high demand for it. But there are some prices that you'd have nobody buy the item. So we're going to think about those relationships today and get into kind of the quantitative aspect of relating demand and price. The general relationships, though, everyone seems to understand that if price increases, demand will decrease. And if prices decrease, demand will increase. All right, now we could graphically represent that. And in the simplest conception, that might just be a straight line. In reality, it's probably a non-linear relationship. But let's just say that this is the relationship between price and demand for a certain product. So a certain product, when the price is high, that's the vertical axis. If you have a high price that you want to charge, there's going to be relatively few people interested in buying it at that high price. But then for the same item, if you have a lower price, there are now going to be more people who demand the product and want to buy it. So there's a continuum there, and if you change your price, you're going to change the amount of demand. And by the way, we could even extend this figure so that it intercepts the vertical axis. And so now think about, if we do that, what does that represent? Oops. If we intercept the vertical axis, that represents what is the price at which there's zero demand. So think about here at the intercept, no demand at some price. Okay, so there's a formula we can use to describe the shape of this line or curve. Some cases it will be nonlinear. Sometimes maybe we can get away with modeling that as a linear relationship. Here we're saying this is a classic y equals mx plus b. You know that general form of a linear equation, y equals mx plus b? So this is that. This is saying the intercept, the vertical axis here, price, is A, which is the intercept, the price at which there's zero demand, minus lowercase b is the slope of this curve. And so it's how much the demand increases for each unit decrease in price. Like if you drop the price of your item by $1, then how many additional people want to purchase the item? So that's the slope of the line. And then D is the units of demand. So how many items are sold? So there's an equation here. Now let's get back to some definitions and terms. Demand is how many units are sold. P is the price. And so if you want to know how much revenue your company is earning, that's simply the price multiplied by demand. Right? If you're selling cars, you sell 100 cars in a month. And if you're selling, the average price of the car is $20,000, then your revenue would be 20,000 times 100. So what is that? 20 million? 20,000? No. Sometimes when you're standing in front of a light, it's hard to do math in your head. 200,000, 2 million, all right? 100 cars at 20,000, your revenue would be 2 million. So it's just price times demand is your revenue. Now remember, price has its own equation. Back from here, we said price, P, is A minus lowercase b times D. So A is the intercept, lowercase b is the slope of the line, and D is the number of units sold. So here, what if we substituted that bigger formula in for price? Then with that formula for price, then revenue becomes this. So it's D times A, and then D times B times D. So AD minus BD squared. So this is just another way to calculate revenue. Sometimes you may have the price function, and if you substitute the price function into the revenue function, then this is how we can calculate total revenue. Either way is fine. Price times demand or this function. So what is revenue? That's just how many dollars are coming in. That's not the same thing as profit. Distinguish revenue from profit. Anybody got a sense for how those two are different? How is profit different from revenue?
Revenue is just the money you make off of what you sell, and profit's what you like actually gain over top of what it takes to produce and
Good.
Or buy what you sell.
Thank you. That's right, Cameron. And Yusuf already had it. Profit is what you take home, meaning after your expenses. All right, so we're just going to talk about revenue for a moment, but keep in your mind that after that, we'll also talk about profit. We could graph revenue, and here is a function of revenue on the vertical axis where we have increasing demand. Okay, so demand, remember, is how many units people want to buy, and it's how many units you've sold. And what this shows is that at first, as your demand is going up, so does your revenue. And that makes sense, doesn't it? Because if you're selling more things, you should be getting more money. So the first part of this curve usually makes perfect sense to people. But what's at first a little counterintuitive is the second part of this curve. So what that's saying is the demand is getting higher and higher, but your revenue is actually decreasing. So help us understand that. Why is it that if the demand was going up, that your revenue would peak and then actually begin decreasing? Why is it that revenue goes down with additional demand beyond a point? This is tricky, but I bet somebody's got it. So don't be shy.
The higher demand, the more likely you are to drive yourself into the ground by trying to make so many for everyone.
Okay, I think that's part of it. Chad said too much product. Well, I guess what I should clarify is that with demand, we assume that all of it is being purchased. So it's not just that you are making the items and they're not being sold. Nick's got it. Nick has it. He just said, because you've lowered prices too much. Think about when you're a manufacturer or a seller, your only lever to increase that demand is to lower prices. So how did the demand get so high? It's because this person lowered the price. And so maybe you're selling a lot more units, but you're getting less revenue per unit because you've got a low price. And so what this shows is that there's a formula for D hat, this little symbol across the top, we're going to call that a hat. D hat is A, which remember was the intercept of the vertical axis. A is what price would it be for nobody to buy the item. Divided by 2B. Lowercase b is the slope of the price line. And that's just simply if you decrease the item price by 1 unit of cost, then how much additional demand do you get? So maximum revenue is not at this low demand, because at this low demand, sure, you have a high price for each item, so that's good, but you're not selling very many, so your revenue is low. If you're way over here, the problem is, yeah, you're selling a lot, which is great, but in order to stimulate the demand, you had to lower your price so much that now you've got low revenue. So maximum revenue is in the middle. Now remember though, we're not trying to maximize revenue, we're trying to maximize profits. And so just because D hat coincides with maximum revenue, that does not mean that maximum revenue is necessarily optimal demand. And so we'll talk about the difference between optimal demand and maximum revenue, but I wanted to point this out and tell you about the relationship. Sometimes on exams, I like to ask concept questions. And probably the most meaningful concept questions are those where I give you a figure and ask you to explain it. So this would be a good one for a test, I think, where I ask you to explain why does the revenue decrease with increasing demand. And so what you need to say is that the way that you got that high demand was by lowering prices. All right, now let's talk about the things we need to understand in order to get to profit, because we've just been talking about the revenue coming in so far. Revenue is your selling price multiplied by the number of items sold. But to make those items, you had to spend money. And broadly speaking, the two main categories of costs are costs that are fixed, meaning it doesn't vary based on how many you're making. So think about Toyota. Their fixed cost for a given month may be the rent on the building that they're using, or the robots they've purchased, or their fixed costs might be the salary of the management workers. Those are all things that whether they make 100 Toyotas in a day or 0 Toyotas in a day, they still have to cover those fixed costs. The variable costs, though, are the expenses that change depending on how many items you're making. So if you make 0 Toyotas in a day, you have no variable cost because you haven't consumed any materials, you don't have your hourly labor on the floor. But if you're making 100 Toyotas a day, now you've got the steel, the rubber, the computer chips, electricity, labor costs. And so the magnitude of variable costs changes based on how many you're making at a time. So those two together give you the total costs. You know, the variable costs could be broken down even a little bit further, because here I was talking about variable costs in a day. You know, like if you're making 100 Toyotas, then your variable costs, if you factor all of the steel and all of the rubber and all the electricity and all of the labor, you know, like maybe you've got $4,000 worth of variable costs for each car that's being made. So this lowercase v is variable cost per unit. It's where you express your variable costs in terms of each item that's being produced. And so the overall variable costs are how many items are being made, demand, multiplied by the variable cost per unit. So it's how much variable costs are tied up in each item that's produced. Okay, now here we are. This is finally what we're trying to maximize. We're not trying to maximize revenue. We're trying to have the biggest difference between revenue and cost, because that's the profits we can take home or that we can reinvest into the business. Maximizing profits should be the objective. And so you want the biggest difference between revenue and cost, and that's how you make big profits. Lower cost, raise revenue. You have to do both. So the optimal demand, D star, is the number of units sold that is associated with maximizing profit. And I'll show you where this formula comes from in just a moment, but you can see it's A, which was the intercept, it's the price at which no items are going to be sold, and V, lowercase v, is the variable cost per unit, and then you divide it by 2, lowercase b, which was the slope of the price demand curve. There's also this formula for break-even points, D prime, and that tells you how many items need to be made to just barely be profitable. And there are 2 break-even points. If you notice in this formula it says plus or minus. And so there's a lower break-even point and an upper break-even point. And let me show you a graph that illustrates all of this, and I'll explain more about the break-even points. Before we move on to that graph, are there any questions so far about the things that we've been discussing? Okay. Here's that curve. We've already seen some of this before. The total revenue curve, that's familiar. Okay, so don't get too intimidated. One of the 3 things that's going on here before, we've already seen, total revenue. So we understand that. CF means fixed costs. And so the reason why that's a flat line is that the number of dollars you spend on the fixed costs isn't affected by the level of production or by the number of items being sold. So you can either make a little or you can make a lot, and your fixed costs don't change. The total costs, though, include variable. So C sub V is the variable cost. And so if you make a certain amount of items, you've got that much variable cost, and the total cost is the fixed, which is below that line, plus the variable. So if you're making a really lot of items, then your variable costs are going to be high. Okay, so let's talk about maximum profit. What we want is the biggest distance possible between revenue and cost. I told you earlier when it was just showing this part of it, we want big profit. Big profit means big revenue, small cost. You want as much distance between those 2 things as possible. So now let's think about it graphically. Here's the curve. We want this revenue curve to be far away from the cost curve. So right here, they're pretty close together. So that's not maximum profit. And look at how those 2 curves are getting further apart as we go along the horizontal axis. So see, at this level of demand, they're pretty far apart. And this is where they're the most far apart. And it happens to be where those 2 curves are parallel to each other. So do you notice that graphically? That the slope of the revenue curve is equal to the slope of the total cost curve at this point. So this formula for optimal demand is just looking for making those 2 slopes parallel. So we want to have lots of profits. So we want to have big revenue, small cost. So here, total revenue, if we just go to the maximum total revenue, that's not as much profit as this D star, which is the optimal demand. All right, now finally, break-even points. What does it mean if we are to the left of D prime 1? I'll pause and give you a moment to answer. If you are making less than D prime 1 units, if your production and sales is less than this, meaning to the left, then what is the interpretation? You're losing money. Brett and Cameron got it at the same time. You're losing money because costs are higher than revenue. So that's not what we want. We want revenue to be higher than costs, and in fact, we want to maximize the difference between revenue and cost. So this first break-even point, anything to the left of it, and you're losing money. Anything between D prime 1 and D prime 2 is profitable. So it's the range of profitable demand. And so the second break-even point, if you get further to the right, the problem is that your revenue is decreasing and your costs are still going up. So the profitable range of demand is between D prime 1 and D prime 2. And so this formula allows you to find those two break-even points. All right, here's our in-class exercise. You may have it printed looking like this. All right, so let's see what we have here. What's the situation? Our company is producing an electronic timing switch. The fixed cost is $73,000 a month, so that's C sub F. The variable cost is $83 per unit. Okay, so that's lowercase v. Variable cost per unit is 83. And then here's our equation that relates price and demand. And let's go back to the general form of that equation. Just remind ourselves what it looks like. Okay, so here's the general form. P equals A minus lowercase b times D. So in the in-class exercise, A is 180. That is the price that if we tried to charge people $180 for that timing switch, no one would buy it. But if we charge even a little bit less, somebody will buy it. The demand will start going up as long as the price is below 180. So that's A. A is 180. And then lowercase b is 0.02. So b is not negative 0.02. The negative sign is in the form of the equation. B is just 0.02. All right, so with these formulas, I'd like you to calculate what is the optimal volume that should be sold. So what's D star? What's the maximum profit that can be made? And then try using this break-even point equation and see if you can find the domain of profitable demand. What's D prime 1? What's D prime 2? And then get some practice sketching that out. And I'm going to, of course, go over the solution with you, but then I'm also going to show you how you could set this up in Excel and create a nice looking chart. But before we do the chart in Excel, I'd like you to try that by hand. You know, like have on the horizontal axis demand, on the vertical axis you're going to have price or revenue. So it's just really amount of dollars on the vertical axis. And then the sketch that you do should look like this sketch, but it's going to actually have numbers associated with it. Okay, so I'm going to put you into breakout groups in case you'd like to discuss this and check answers with one another, and then we will reassemble in about 12 minutes to go over the solution together. Welcome back, everybody. Let's take a look at the solution and just see if there are any questions. Oops. Did I close it? Okay. There we go. So you can see that what I've done is I've labeled our variables where the fixed costs are $73,000 per month. The variable cost per unit, in the slide that I'm showing you here, the variable we're using for that is just lowercase v. In a previous text, it had a slightly different variable assignment. So here I'm calling it C sub v. That means the variable cost per unit. You'll notice that I substituted it in the numerator here after subtracting out the A, the intercept price. So what you should get is the optimal volume, the number of units that's going to result in the most amount of money for you is if you sell 2425 units. Okay. Now the maximum profit is going to be the revenue minus the costs. And so our revenue, if we're selling 2425, we can find out what's the selling price that's associated with that. And so the revenue is simply going to be the selling price at a certain level of production multiplied by the number of units sold. So we'll have incoming amount 318,887.50 cents. And then the outgoing costs includes the fixed cost and the variable. So together, when we take into account the fixed cost of 73,000 and then each unit costs us $83 in variable costs, and we're selling 2425, so the combined cost is $274,275. And so then therefore, here's our overall profit. It's the revenue that we've earned at a certain level of production minus the costs. So the most revenue we can make, given our understanding of the market and giving our understanding of how much volume people are willing to buy at a certain price, $44,612.50. Now the tricky thing is using this formula for the break-even points. So we have to be really careful with the substitutions there. The approach that I use, don't try and just put it all into your calculator. You'll inevitably make a mistake if you try to do it all at once in your calculator. I think it's far more reasonable to write out the formula and then each one of the substitutions and then start combining things together in groups. So you can see, for instance, here I've got the 180 minus 83, and that's negative 97 because of the minus sign in front there. And in the denominator, I've multiplied the 2 by the negative 0.02. And then the entirety of what's inside the brackets here, once you take it to the 1/2 power, which is easy to forget, so don't do that, plus or minus 59.75 and 74. So 932 units is the beginning of our profitability, and 3918 is the end of our profitability. And if you sketch what that might look like, then here is that figure and what it looks like. All right. Well, it's 12:47. I'd hoped to just basically show you how we could set this up with Excel, but that's not necessarily something you have to do. It can be solved by hand. But let's just take one last look at the announcements before we part ways for today. Homework 11 is due before class on Friday. So if you have any questions about those two problems, it's a small one, but if you have any questions, let me know. And I hope that you're also spending some time working on and thinking about the project. So that's it for today, everybody. Hope you have a good one. And I'll see you on Friday. Aaron has a suggestion that I should make a video on how to do it on Excel, and I'll follow that suggestion. I'll do that right now, and I'll email you guys the link of the video. Yusuf asks about the time, and that's a good question. You know, in the example we worked today, it wasn't, oh, okay, so this was saying per month. So we were doing this on the basis of a month, and so we wanted to know how many, this would be the optimal volume in a monthly period, because this pricing, the fixed costs were expressed on a monthly basis. Good question. All right, take care, everybody.